Hello and welcome to the Oxford Discrete Maths and Probability Seminar. This week it's a great pleasure to have Paul Seymour from Princeton, who's going to talk on a log-log step towards the Erdős-Heinel conjecture. Thanks.
Okay, thank you. I'm talking about a problem that the four of us worked on a couple of months ago. Matija Buček, Alex, and my student Tung Nguyen. And it's a problem about induced subgraphs. It's about the Erdős-Heinel conjecture. But so I'm a bit worried about this talk, to be honest, because it's a lot of detail, and Alex had to drag me kicking and screaming into giving this talk because I'm afraid it's too much detail. But I'm going to try and convey it. I want at least to convey the main idea. I want to give details of the proof of the main lemma, and I'll try to sketch everything else, and we'll see how it goes. And if it all falls down, please blame Alex. So it's about induced subgraphs. So let me start with the Erdős-Heinel conjecture itself. So an induced subgraph means a subgraph you can get by deleting vertices. You have a graph, you pick some of the vertices, and you keep all the edges of the graph that have both ends in that subset. That's an induced subgraph. And we'll say a graph is H-free if it doesn't have any induced subgraph isomorphic H. And some notation. Alpha is the size of the largest stable set or independent set, and omega is the size of the largest clique. You can make graphs where the largest clique and largest stable set are only log of the size of the graph, but it changes as soon as you exclude any induced subgraph. It's known that it changes as soon as you exclude any induced subgraph. You can get much larger cliques and stable sets. So, for instance, if you exclude the four vertex path P4, then max of the largest clique and stable set is square root of the number of vertices. If you exclude KT, then there's this formula. You get a large stable set. You can't get a large clique anymore because you've excluded KT, but you get a large stable set. If you exclude the bull, you know the bull is a triangle with two horns growing off two vertices of the triangle. If you exclude that, then you get clique-stable set of size at least g to the quarter. This is a theorem of Maria Chudnovsky, Muli Safra. And there's, if you do C4, Erdős and Heinel proved that if you exclude I believe Erdős and Heinel proved, yes, they did. If you exclude C4, then you get a clique-stable set of size g to the 1/3. And notice it's not log g anymore, it's powers of g. All these things say if you exclude something, there's a clique-stable set of size, a power of g. And that's the conjecture. So this was a conjecture from 1977 that for any graph, there is some constant c, depending on h, so that if you look at H-free graphs, they all have big cliques or stable sets. Cliques or stable sets of size g to the power c. And it's an old conjecture. I mean, 1977 is a while ago now. And it's still not known for very many graphs, and it might be false. I mean, as I keep working on it, I'm becoming more and more persuaded that it might very well be false. But let me tell you what it's known to be true for. Let's say a graph has the Erdős-Heinel property if the theorem is true for it. So if when you look at H-free graphs, H has the Erdős-Heinel property. If when you look at H-free graphs, you get big cliques and stable sets. It's known that if you do substitution, if you take two graphs that have the Erdős-Heinel property and you substitute one for a vertex of the other, then the bigger graph you just made also has the Erdős-Heinel property. What's substitution? I mean, you take H1, you can see my mouse, right? You take H1 and you take a vertex of H2 and you replace this vertex by this subgraph. In other words, you delete the vertex, you add this subgraph, and you make all the vertices of the subgraph adjacent to the people that used to be neighbors of the vertex, so in this picture. That's vertex substitution, and you can keep repeating it, of course. So that gets you at least infinitely many graphs, but that's about the list. So what's known is Erdős and Heinel proved P4 free graphs have the property. And the substitution is Allen-Pak-Solomoshi. That's anything you can make by substitution from smaller graphs with the property also have it. Chudnovsky and Safra did the bull. 4 of us did the cycle of length 5, which we were very pleased about because people had selected the cycle of length 5 as a case that the conjecture was probably false for. So it came out to be true for the cycle of length 5. But that's unfortunately the end of the list. That's all the graphs it's known for after, what is it, 45 years? That's not very convincing evidence that the conjecture is true. And I don't know, I might be false. We've worked very hard on whether P5 has the property, the 5 vertex path, and it's still not known. There's a new result just this year, not by us, by Matija Bucic and Blanco, that they didn't prove the conjecture, but they proved something quite good, that you can get a Kleeko stable set of this size, 2 to the power C log G to the 2/3 for P5 free graphs. But I just wanted to mention that because it's a new result. The trouble with slides is when I go on, you can't see what I just showed on the previous slide. So slow me down if you want to see what's on the slides. Oh, and also please do ask questions if you have questions. I don't want to just wait to the end for questions. If you have any questions, please just interrupt. So unmute yourself and interrupt. A cograph is a P4 free graph, and cographs are very simple, very easy graphs. So the graphs you can make starting from one vertex graphs by taking disjoint unions and taking disjoint unions in the complement. In other words, taking 2 graphs you've got and making all these vertices adjacent to all those vertices. And let's define mu of G to be the size of the largest induced cograph in the G, in G. Working with mu of G is somehow more convenient than working with the max of alpha and omega, because, well, first of all, it's equivalent. If you can restate the Erdős-Heinel conjecture in terms of cographs this way. You just say there's a constant such that mu of G is at least a power of G for every H-free graph. And that's equivalent because if you've got a large cograph, then you have a large Kleeko stable set, because cographs have Kleeko stable sets containing square root of the number of vertices. And conversely, if you have a large Kleeko stable set, you've got a large cograph because they are cographs. So you can state it in this language, and it turns out to be easier. The reason it's easier is if you take you'll see. Too hard to explain it all. But so what is known? What this talk is about is not really the Erdős-Heinel conjecture itself, but what can we prove about how large a Kleeko stable set you get in an H-free graph? Erdős and Heinel proved you can get 2 to the C square root log G. And that was in 89. Actually, they proved it, I think, earlier, and they wrote two papers in this. They mentioned it in their earlier paper in the mid-70s, but they didn't put the proof out till 1989. And we've got an improvement. It's a very small improvement, but it's an improvement. And it's the first improvement since 1989 on this well-known theorem of Erdős and Heinel. We put a log in the exponent there. So just to put everything in perspective, let me say these things again. So the Erdős-Heinel conjecture says that mu of G is, there is a C such that mu of G is at least 2 to the C log G. In other words, it's at least G to the C, if you think of logs is base 2. Erdős and Heinel proved mu of G is at least 2 to the C root log G. And we've proved mu of G is at least 2 to the C root log G log G. A bit better. And I think my first task is to persuade you what a natural theorem this is. Let me first attempt to do that. So how can we prove it? I need some terminology now. Say two disjoint subsets are complete if every vertex here is adjacent to every vertex there. Two disjoint sets of vertices are complete to one another if every vertex of the first is adjacent to every vertex of the second. And they're anti-complete if there's no edges between them, if the reverse is true. And it's a pure pair if it's either complete or anti-complete, just for having a word to say it. Suppose we could prove that when you're looking at H-free graphs, suppose we could prove that they have linear size pure pairs. Suppose we could prove that every H-free graph has, again, suppose we could prove that there is C, such that for every H-free graph, it's got a pure pair AB where both A and B have size at least constant times the number of vertices. Suppose you could prove that. Then you can prove H has the Erdős-Heinel property, because what you do, you look at, I've got my graph. I don't know if you can understand my hand waving. Can you see me? Okay. Suppose you, all right, let's try and do this in the air. So here's my graph. I have two subsets A and B, both of linear size. And they're either complete to one another or they have no edges between them. Now you can apply induction. This induced subgraph has a large cograph. This induced subgraph has a large induced subgraph. And the union of these two, a large cograph that's an induced subgraph, and the union of these two cographs is still a cograph. That's the point about cographs. Either they're complete to one another or there's no edges in. In either case, the union is still a cograph. So you end up with a cograph of double the size. And now we have to figure out how large do I need the pure pair to be to make this induction argument go through. And it turns out, if you really want to prove Erdős-Heinel, you need A and B to have linear size. And that looks like a promising argument that unfortunately is never true. That it's not true that every H-free graph has a pure pair with A and B of linear size, unless H is really small, unless it's only got most 4 vertices. So, but still, it's an idea. What can we do with that method? I mean, now we're not trying to prove Erdős-Heinel, we're trying to prove something weaker. We're trying to prove the Erdős-Heinel theorem, not the Erdős-Heinel conjecture. We're trying to prove we're trying to improve on the Erdős-Heinel theorem. So maybe we don't need them to be of linear size anymore. And that's the approach we're going to take, or nearly the approach we're going to take. So how does it work out? If you could always get a pure pair with size at least G over some power of mu. By the way, in this talk, we'll be looking at sets that are linear size, meaning an honest constant times the number of vertices. And we'll be looking at sets that are nearly linear, meaning the size of G divided by a power of mu, with a constant power of mu. And think of, we're trying to get mu to be a polynomial in G. So you can assume mu is really small as a power of G. So mu to the K is really small as a power of G. G over mu to the K is almost G. It's G to the 1 minus epsilon, where epsilon is very small. So this is a nearly linear set. And all the sets of vertices we look at in this talk will be either honestly linear or nearly linear. And at some stages, I'm going to be skipping the numbers. I'll just be saying this is a nearly linear set. And this is what I mean. It's G over a power of K, the power of mu. If you could get a pure pair where both sets had size G over a power of mu, then you can prove the Erdős-Heinel theorem. I mean, there's a calculation to do there, but it comes out. If you can prove there's always a pure pair where one is nearly linear and the other is honestly linear, then you get what we proved, 2 to the C root log G log log G. Again, it's this induction. You apply induction to this part, apply induction to that part, and say the union is still a cograph, and what have we proved? And if you go through all the numbers, this is what comes up. You have to figure out what function is this a proof of? What function of G does this prove that mu is at least f of G? Unfortunately, I don't know if these things are true. I mean, this is not how we proved our theorem. It's some evidence that getting this log is going to turn up in natural places, but this isn't actually what we did. Let me say a pair is almost pure if every vertex in B has very few neighbors in A, or either that or every vertex in B has very few non-neighbors in A. So very few, I mean A over twice mu. The number of vertices for each vertex in B, the number of neighbors it has in A is at most A divided by 2 mu. So it's a very small fraction of A. Or maybe the complement. All these things will turn out to be invariant under taking complements. So almost pure pairs are much easier to find, and they're as useful as pure pairs. So why is that? Because you can still do the same induction. You pick a cograph in B. By induction, B has some big cograph. Now you look at all the vertices. Let's say we're in the first case. Every vertex in B has very few neighbors in A. So now you look where are those neighbors? I mean, this cograph we've chosen in B, it's only got size at most mu, and all its vertices have only A over 2 mu neighbors. So altogether, they've only got A over 2 neighbors at most. So the left end of these edges I've drawn only contains half of A at most. You've still got half of A, which is free and clear, has no edges over to this brown subgraph. And now you can choose a cograph inside of that by induction. And again, take the union, and we're back in the same place as before, and doing it with an almost pure pair instead of a pure pair. You don't really need that the pair is pure. You can tolerate a few edges between them as long as it's not very many. You can still do the same argument. So let's run through those things I said before, and let's do it again. What if I had an almost pure pair? Linear. Well, again, you could prove that H has the Erdős-Heinel property, but it's still only true for very small graphs. It doesn't get you any further. What about the next case? If you had an almost pure pair where both sets outside G over a power of mu, then again, you could get, as before, you could get the Erdős-Heinel theorem. Now, this one is actually true, and this is how Erdős-Heinel did it. I mean, I don't know if it's true that you always get a pure pair of that size, but it is true you always get an almost pure pair. And if you get an almost pure pair where A is G over a power of mu and B is honestly linear, then you still get this this expression 2 to the C root log G log log G. I would like to be able to say this is how we did our theorem, because that would fit it nicely into the talk. It's not actually what we did. It's a bit like what we did, and it will come up in the proof, but it's not exactly true. And I don't know if this is true, but we're getting closer to what we actually did. This is what we actually did. Instead of taking 2 sets, what if we took 3 sets? What if we had a pure triple? Well, it would come out to be the same. You get the same answers. You know, a triple is no better than a pair if you're trying to do induction. It changes the constants a little bit, but it's not a significant change. Any constant number of sets is no better than 1 set. But what if you had a lot of sets? What if you had, it wasn't just a constant number of sets. It was something like something in some function of mu. So if mu is large, you get. Suppose the number of sets is allowed to be a function of the things we're trying to optimize. Then it's helpful. And that's what we're going to look for. We're going to look for many sets, all of size. Okay, there's 2 things I've done here. One is I've changed 1 over 2 mu to X. Because after this slide, we're not going to need mu anymore. Everything I say is true for a general variable X. But in the statement of this theorem, think of X as 1 over 2 mu, because that's what we're going to need in the application. So what am I looking for? I'm looking for a whole lot of disjoint sets. Pairwise, the almost pure, nearly pure. What did I call it? Nearly pure? Almost pure. They're pairwise nearly pure. And the size is x to the k times g. In other words, g over a power of mu. So it's like what Erdős-Heinl did, except for we're getting lots of sets instead of 2. And the number of them is going to be log of 1 over x. And we need more than just pairwise that they're almost pure. We need that, it's a stronger statement, that for each I, either all the vertices here have very few neighbors in AI, or all the vertices here have very few non-neighbors in AI. So it's this whole subset that's almost pure to AI for each I. Is it clear that it's important? I mean, you need to grasp this because this is what the whole talk is about, proving this theorem. It's worth me spending a bit more time trying to make sure everybody at least understands what we're going for. Has anybody got any questions on this? And as I say, please ask questions at any time, but you understand what I'm going for? That if you look at H-free graphs, for any graph H, you look at H-free graphs, and you choose any number x, small enough, then you can get a sequence of disjoint subsets, all of size at least some power of x times the number of vertices of G. And the number of them is log 1 over x. With this almost pure property, this sort of interval almost pure property. Let me show you again how that's going to be helpful. To get our application to the log-log stuff, we need to take x to be 1 over 2 mu. But from now on, we won't need to use that fact, just 2. But suppose x is 1 over 2 mu. Now let's get a big cograph out of this thing. Inductively, we're looking at H-free graphs. So these subgraphs are also H-free. If I look at AN, it's also an H-free graph, and I can say by induction, it's got a large cograph. And let's suppose inductively we proved that the union of the brown things is a large cograph. Now let's make it even bigger by adding a bit of AI. This is the cograph. So its size is only mu. So once again, you can look at where the edges coming out of it go to. They only cover half of AI. So in the other half of AI, I can choose another large cograph. And it's still true, the union of all the brown stuff is a cograph. And you do the calculations and it comes out what you've proved is this log log G thing. And the calculations are terrible. That's really unappealing aspect of this work, getting from these pure pairs to what function of G have you proved alpha and omega is at least, is a real nasty calculation, and it's not the fun bit. I'm leaving that out. I need to modify this theorem a bit. So first, we're going to prove this by, sorry, let me go back. We're going to prove this theorem by induction on H. Now, to make it work, so notice here it was important, in this application, it was important that we were talking about H-free graphs, because I wanted to say this part is also H-free, and so it's got a big cograph by induction on the number of vertices. And so is each of the individual blue boxes. But to prove the theorem, we need to prove a stronger theorem where we don't assume it's H-free. We assume it's got a few copies of H. So let's have this notation. End of G means the number of induced subgraphs, number of copies of H in G, number of copies of H that are induced subgraphs of G, number of isomorphism from H to induced subgraphs of G. And I just want to assume that not that G is H-free, but that the number of copies of H is only a small power of what it could be. I mean, it could be at most G to the H. If every single subset of size H gave you a copy of H, if every subset of vertices of size H gave you a copy of H, you get something like G to the H. But if it's only a small fraction of that, if the number of copies of H in G is only X to the K1 times G to the H, and that's a much weaker assumption, right? I mean, we're just saying that the density of copies of H in G is not really large, then you get the same conclusion. And I'm going to have to modify it a little bit more. But actually, no, this will do for now. So now there's a key lemma we use to prove this theorem. I mean, so now on the whole talk is about proving this theorem, but some of the details I'm going to do, some I'm not. And the important part is there's a lemma, which is a really nice idea. And I want to do that in detail, and then I'll sketch how we use the lemma to prove this theorem. Is everybody okay so far? Let me tell you the lemma. So suppose I've got two sets A and B, and suppose I tell you every vertex in A has at least a few non-neighbors in B. I'll say it more exactly in a minute, but suppose everybody in A has at least a few non. The union contains many copies of H. Oh, there's something going with the. Can you hear me? The internet connection's going funny.
It's fine now. We lost you very briefly.
Okay, so suppose
back to the top of the slide, that would be great.
Sorry?
If you could restart, if you could go back to the top of the slide, it should be great.
Okay, so I'm giving you an idea of what the key lemma says. So choose a graph H and choose some special vertex of it, G. Now, and suppose I've got a graph and I've got two sets A and B. And suppose every vertex in A has a moderate number of non-neighbors every vertex in A has a moderate number of non-neighbors in B. Then maybe you contain many copies of H. Or maybe there's a subset B prime of B, which is still a reasonable size, such that this contains very few copies of H minus the vertex G. Or you can get two subsets, A prime, a reasonable amount of A and a reasonable amount of B, such that there's very few edges between them. So notice we started with the assumption that every vertex in A had at least a reasonable number of non-neighbors. The A and B might have been very dense to one another. It might have been every vertex in A is joined to 99% of B. I'm not saying that there's any suggestion of, we're not saying sparsity in the first place. We're just saying nobody's joined to almost everything in B. Certainly everybody in A, we're happy if everybody in A is joined to half of B, that's fine. We're joined to 99% of B, that's fine. We just want a few non-neighbors. Everybody has to have a few non-neighbors. And then one of these three things is true. Either I've got lots of copies of H, or I've got only a few copies of H minus G inside of B prime, or I can shrink them so that there's very few edges between A prime and B prime. That's what the key lemma says. And that's the new idea. This is sort of surprising, right? You can go from having just a few non-edges everywhere to almost no edges and not shrinking the sets too much.
Does copy mean induced copy?
Induced copy means induced copy. Everything here is induced copy.
Mm-hmm.
Now you understand I'm now going to state the key lemma exactly, and it looks a bit more formidable, but I think it's best if you get the idea from this slide, and then I'll go to the next slide where the lemma is stated exactly. Are you happy with the statement that either you contain many copies of H, or you can shrink to some B prime which contains few copies of a smaller graph, and then we'd apply induction, or you can shrink A and B so that you get very few edges between them. So once again, this is what it really says. Start with a graph and you choose a vertex little g of it. And we're going to fix two numbers B and C and define A to be this, just some constant. Now you start with a graph G, and A and B are disjoint subsets, and X is some number, not too big. And suppose every vertex has at least X times B non-neighbors. X can be very small. So every vertex in A has at least X times B non-neighbors in B, but still every vertex in A can be almost complete to B, but not completely complete. Then either the number of copies of H in G is at least this big, or there's a subset of B, still a reasonable fraction of B itself, so the number of copies of H minus G in that subgraph is small. Or you can shrink A and shrink B to sets of decent size still, such that the number of edges between them is very small compared with what it could be. The density of edges between them is very small. And I'd like to show you the proof of this in detail, because this is the sort of nice idea that made everything else work. And first I need to modify it a bit. So we used to say in this version, all we need from this theorem is that the number of copies, this first bullet says the number of copies of H is big. But to make the proof work, we need to prove something stronger. We're going to prove we get at least that number of copies of H in G, where little g is mapped into A and all the rest is mapped into B. If I was really lucky, I mean, the maximum number of isomorphisms of this kind I could get is where G goes into A and everybody else goes into B. It's at most A times B to the H minus 1. And I'm saying at least I've got a sort of fraction of them, X to the A times the maximum number I could possibly have. Or the other two conclusions are the same. I get a subset of B prime, not too small, with very few copies of H minus G. Or I can shrink the two sides to get very few edges between them. Now I have to change it one more time, because I've got this special vertex G in H, and I want to figure in the degree of G. So this is the same statement I just took the red out, but now I'm going to change the first bullet again. Let the vertex G of H have degree D. Then we're going to prove this statement. And this is stronger than what we proved before. I don't think you can see that by me flipping back and forth between these two slides, but it's a stronger statement than we were proving before. You get the previous statement by saying D is H minus 1. And this is helpful because we're going to do induction on D. So are we okay with the statement? Shall I go on with the proof? Okay, let's try. Stop me if you get lost. So we're proving this statement by induction on D. And the first case is D is 0. So I'm looking at a graph. I've got my graph H has a part H minus G, and I have a vertex G with degree 0. And I want to count isomorphisms where all this part goes into B and my isolated vertex goes into A. So now choose any vertex in A and look at its neighbors in B. It might have neighbors, but it's got at least a moderate amount of non-neighbors. That's our hypothesis. There's a moderate amount of non-neighbors. There's at least the number of non-neighbors of V is at least X times the size of B. And how many copies of G minus B of H minus B can I get in size of B prime? Well, if I can't get very many, that's an outcome of the theorem, right? That's the second outcome. There's a B prime of this size, which doesn't contain many copies of H minus G. So we can assume we did contain many copies of H minus G. But any copy of H minus G here, I can add V to it, and that gives me a copy of H. And so just for every vertex H, I've got this many copies of H where little g is mapped to V, and all the other vertices are going to B prime, in fact. And that's all we wanted to prove. So now just sum over all V. This is true for all V in A. So just now, if I want to count the total number of copies of H, I can just sum over all V. And I get the same thing multiplied by A, which is what we needed to prove. So the case when my vertex G of H has degree 0 is easy. It just sort of falls out immediately from the assumption that every vertex has a good number of non-neighbors, and the non-neighbors contain lots of copies of H minus little g. But let's do the general case now. Assume now I've got degree bigger than 0. And pick an edge. Pick an edge coming out of this and delete it. Now the theorem's true for this graph where H minus little e. So I've got lots of copies of H minus little e where G is mapped into A and all the rest is mapped into B. Let's call, I don't want to keep saying G is mapped into A and all the rest into B. Let's call these good copies. So by induction, we got this many. And notice I've changed D to D minus 1 because in H minus little e, the degree has gone down by 1. I mean, there were 3 outcomes of the theorem, right? But if either of the other 2 outcomes holds for H minus E, then it also holds for H. So I can assume the third outcome, whatever the outcome was, this is the second outcome holds. No, the first outcome holds. First outcome holds for H minus little e. All right, so let's think what that means. I've got lots of copies of H minus little e. So what's H minus little e? I hope I have a picture here somewhere. Yes. How do you make a copy of H minus little e? You need a copy of H minus G in here and a vertex in A that's got the right adjacency in this part of the graph, which is H minus G and the vertex little h. Need to draw a picture. Don't think this is good enough for this. No, I'm going to wave my hand. Okay, remember what H looks like. We had a vertex G. We chose a neighbor of it, little h. We deleted that edge. So the graph we got many copies of, H minus E. It consists of the part you get by deleting both G and H, and plus a vertex that represents G and a vertex that represents H. So if I'm looking at a copy of H minus little e, it consists of a copy of H minus G and H, and a vertex somewhere in B that's got the right adjacency to this, and a vertex here that's got the right adjacency to this, where these two are non-adjacent. So let's look at all the possibilities. Fix a copy of H minus these two special vertices. And let's look at all the ways you could extend that copy to a copy of H minus G. These are all the vertices you could add to that. So people that have exactly the right adjacency to this subgraph to give you a copy of H minus G. So all these vertices have exactly the same neighbors in C. And look at all the vertices in A you could add. These are all, again, all the vertices over here that when I add them to C, I get a copy of H minus little h. Again, they've all got exactly the same neighbors in C to give a copy of H minus little h. Now, how many copies of H minus E does this extend to? It's the number of choices of a vertex there and a vertex there that give you a non-edge. And we know we've got lots of them. So here's the same picture. We know on average, over all copies of C here, over all copies of H minus these two things, you get at least that many non-edges. I mean, we know altogether we get lots of copies of H minus little e. So averaged over all choices of C, we get at least this many. At least that many. That's if every subgraph of the right size gave us a copy of C. We'd still get at least, the average would still be at least that many. I mean, the truth is the average is much bigger because not every subset of this of the right size gives you a copy of C. A copy of H minus these two vertices. So on average, there's lots of choices on average over C, there's lots of choices A prime and B prime. There's lots of A prime and B prime are big sets. There's lots of non-edges between them. I've got at least that many non-edges between them. So that tells me on average, A prime is at least A times this quantity, because B prime can't be bigger than B. And the total number of non-edges is only A prime times B prime at most. So A prime has to be at least this big. Right? I'm trying to draw a circle here with not containing B, but containing all the rest. A prime has to be at least that big. And similarly, B prime has to be at least this with the A term drop. So on average, A prime and B prime themselves are big sets. So let's leave out all the choices of C where the number of non-edges we get between A prime and B prime is only half the average. And you're only going to lose half of the good copies of H minus E. So, and if I just look at the copies that remain, that survive, that they're easier to count. So now for all the surviving C, A prime is big and B prime is big. And if you do the calculation, that's at least X to the A times A, and this is at least X to the A times B. Now, so what's going, look at it again, look at one of these copies of C. If I have very few edges between A prime and B prime, that's what we wanted to prove. Remember what we're proving? If I go back to Miles, where the theorem says, we have this third outcome. There's an A prime in A and a B prime in B. They're not too small, and the number of edges between them is only that. And that's exactly what we're going to get here, wherever it is. So if for some choice of C, there's not many edges between A prime and B prime, if there's only that many edges between them, then we win. That's the third outcome of the lemma. And otherwise, you always get for every choice of C that survives, there's lots of edges between them. But any edge between them gives you a copy of H, not a copy of H minus E. So that means we get lots of copies of H. And that can't happen because we don't have many copies. Well, I mean, I forget if that was a hypothesis or a conclusion, but somehow or other we win if we end up with lots of copies of H. I don't remember now whether we assumed in the first place that we did not have lots of copies of H, but in any case, if we get lots of copies of H, that's a win. So once again, you look at C where the sets A prime and B prime are big. If there's very few edges between them, then that's the second outcome. That's the third outcome. If for every choice of C, you get lots of edges between them, then you get lots of copies of H. That's the first outcome. And that's the proof of the lemma. Okay, now, was that reasonable? Did you understand that? Let's try. Are you happy with that? All right, let me show you how it's used. So now it's more straightforward how to take in. What does this theorem say? We're going to be, remember what we're trying to prove. If I can go back to wherever here's our theorem. This is what we're actually trying to prove. That if you look at a graph that does not have many copies of H, then you get all these disjoint subsets with a density property, and they're not too small. That's what we need to show. Now, what does this? The lemma says either we have lots of copies of H, and that's great because we could use that here because we know here we don't have many copies of H. The second outcome of the lemma says I can focus on a subset where I don't have many copies of H minus G. And if that ever happens, we'll just move to that subset, replace H by H minus G. And now we can prove this theorem with H replaced by H minus G, because in that subset, we still don't have many copies of H minus G. So we can still get the same outcome. Change all the constants, but it still works. I mean, it's fair to change all the constants because now the graph we're excluding is a smaller graph. It's not H, it's H minus this vertex. So the lemma has three outcomes, and two of them are wonderful for us. Two of them are immediate win. one outcome says we've got lots of copies of H, and that's a win. Second says you can go to a big subset where there's not many copies of H minus G, and that's a win because we just move to it and use H minus G instead of H. So it's the third outcome we can assume we always get. Whenever we apply this lemma, we always get the third outcome. So in other words, if you have two sets where everybody in A has a moderate number of non-neighbors in B, then you can shrink them, not too small, so that there's almost no edges between this and that. And that's very powerful. I mean, and so far it doesn't say anything about log-logs. It's a general lemma. I mean, we were kind of hoping it might actually prove Edersheimel for it, but we couldn't prove the conjecture for us, but we couldn't do that. But there's nothing inherent about this that says you can only prove there's log-log improvement. Maybe we can get better than that, but we don't see it at the moment. But anyway, let me show you how to at least deduce this theorem from the lemma. I need what we're calling approximate blowups. So here's some graph, some little graph, and here's my big graph. And an approximate, for each vertex, you pick a subset, and the subsets mustn't, I care about the size. I want all the subsets to be the same size. So they're all size T, let's say. So for each vertex, you pick a subset. The disjoint subsets, they're all size T. And I want, whenever there's an edge here, then this pair is very dense. And whenever there's a non-edge, this pair is very sparse. So by very dense, I just mean that every vertex here is, so if whenever you look at an edge, every vertex has very few non-neighbors in, every vertex here has very few non-neighbors there, and vice versa. Whenever there's a non-edge, every vertex here has very few neighbors there, and vice versa. So that's just a blow up. I mean, it's nearly what you get by substituting subgraphs for vertices of J. If you do the vertex substitution, you end up with sets where for every two sets they're a pure pair. So I'm not asking that they're pure pairs. I'm saying they're almost pure. They're either very dense or very sparse. You can't, if we're looking at a graph G that doesn't contain many copies of H, it can't contain a blow up of H where the sets are big. It can't contain a TQ blow up where T is big and Q is small because you get too many copies of H. I mean, pick random vertices, one from each, and with high probability, it's going to give me a copy of H because every vertex has, it's got the, and whenever I want this to be an edge, every vertex here has got a very good chance of being adjacent to the vertex I've selected from AJ. So with high probability, the edges come out right, the non-edges coming out right. So if you have a blow up, you've got lots of copies of H. So we can't, if G doesn't contain many copies of H, I can't get a blow up of H in G where the sets are big. But let's choose an induced subgraph of H, maximal such that you've got an approximate blow up. And I have to be a bit more careful about what do I mean by an approximate blow up. I want a blow up, TQ blow up, where T is some constant times G, and Q is some power of X. And not a constant times G. X to the R, X to the some power of X times G, and Q is just some power of X. And R1 and R2 will depend on J. As we get bigger and bigger blow-ups of bigger and bigger subgraphs of H, these constants will get weaker, and we won't demand so much when the subgraph we're getting a blow-up of is getting bigger. So we're allowed to relax, but let me not get into what the constants actually are. So choose a vertex. We know that J is not H, so choose some vertex I, which is a vertex of H, not a vertex of J. Here it is. So this is another vertex of I, a vertex I, which is in H, but not in J. And I've already chosen, this is my maximal subgraph of H for which there's an approximate blow-up in G. Now let me try and enlarge it to get a, I want to find a box that represents I as well to give me a blow-up of this bigger graph, and that'll be a contradiction. So let's try and do that. So case one, there might be a subset here that's very sparse to one of these AJs. It's very sparse to one of the AJs. And it's got linear size, maybe, this over 100 or something. I mean, honestly linear, not almost linear. I mean, really linear. There might be a subset here where that's, say, very sparse to AJ1. Well, what can we do with that? What we can do with that is drop everything. From now on, everything we do will be inside of B. Start the whole proof over again, but working inside of B. What have we gained? Notice that in the theorem, we're trying to generate the sequence of subsets. Well, we would have now found A1, because everything else we're going to get is inside that brown set, which is very sparse to A1. So that's the first term of our sequence. A1 is big enough to count as a term in the sequence. So again, if there's a linear set here that's very sparse to one of these blow-up sets, we'll just drop everything, replace G by this subset, and start the whole proof over again. Start trying to find a blow-up of H inside of B. And we can't keep hitting this case because we'll just grow a longer and longer sequence. If it happens log 1 over X times, then we've won. So eventually, when it's not, and if it doesn't happen log 1 over X times, then these sets don't get too small by this process. They're still a reasonable size. We can still do the calculations the same. So that would be good. So we can assume that almost everybody here, it's not really sparse to any of the A's, and it's not really dense to any of the A's, which is the setup we needed to apply the lemma. The most vertices out here, they've got a moderate number of neighbors in each AJ, and they've got a moderate number of neighbors, non-neighbors in each AJ. Well, all right, so now here we go, apply the lemma. We can shrink this set to some subset. Again, it's not shrunk too much. It's only a power of X it's shrunk by. And AJ1 shrinks again by a power of X to DJ1, where there's almost no edges between these. Or maybe there's almost all edges are present between these. And we get to choose. I mean, if I'm for this particular graph I've drawn, I need my new box. I'm trying to construct a box out here that represents I. So I need it to be sparse to J1. So I'd be looking for people with almost no edges here. And we'd use the fact that everybody has got a moderate number of non-neighbors in AJ. And then we can shrink this so that these two sets have almost no edges between them. And now we start working with this pair. We start working with this set and AJ2. And again, apply the lemma. We get to shrink this one a bit more. And we get a set there where this pair is very sparse. And still this pair is very sparse. I mean, sparsity is it depends exactly how you define it. We can say that sparsity means there's not very many edges between them, or we can say everybody in one set has very few neighbors in the other. And it's almost the same. But if you've got the weaker property, just that the number of edges is small, you can shrink the sets a bit more to get rid of any sort of outlying vertices that have more neighbors than you like. So it really doesn't matter which density or sparsity I use. But in my big brown box here, everybody was sparse to DJ1. Sorry. Everybody is sparse to G1, so they're still sparse when I shrink. And now they're all sparse to DJ2 as well. And keep repeating. You just keep shrinking and shrinking, and you get a subset of each of them. And that's the, oh dear. I'll put this on mute. I call this AJ, and that's my new box that represents I. I've now got a blow up of this bigger graph. That's a contradiction because we already chose J to be the biggest subgraph of H that we get an approximate blow up on. So as soon as you can get, okay, I got myself confused. This phone call's really thrown me. I think that's the end of the proof. Have I said everything? Again, I choose J maximal such that we have an approximate blow of it in G. Here's another vertex. Let me choose another vertex of H, and I will try and get that. And the vertices out here have at least a moderate number of neighbors in each of the AJs and a moderate number of non-neighbors in each of them. And now I can shrink to either make them really dense or really sparse, whichever I want. And so I want my new box to be really sparse to these three and really dense to that one, if I want to get a box that's going to represent I. But you can do it either way around. That's what the lemma says. And I wrote the lemma to produce a very sparse pair, but it's also true in the complement, right? If you don't have too many neighbors, if you don't have if you have at least a moderate number of neighbors, you can shrink the pair to make them really dense if you want. Anyway, all right, that's the proof, I think. I think I should stop there. We had some extensions to Rödel's theorem, but I think I'm not going to bother you with Rödel's theorem. Let me stop at this point. Thanks.
Okay, thank you very much. Do we have any, before we give some applause, do we have any questions?
Just going to say, in all the inductions, you think of X as constant, as fixed, and then do the induction, and then later you choose X to be the right thing somehow. Is that right?
X can be anything. Yeah, that's right.
Yeah. And the other thing was you have this logarithmic number of things. I mean, I guess that's just what comes out of optimizing the calculation, or is there some reason why it's that? I mean, logarithmic, not in N, but in X.
The sets keep shrinking. There was the case when.
Oh, I see. Okay.
When I moved from G to B, and now the number of vertices G has gone down by a constant factor, so I can't afford to do that very much. But I can afford to do it log 1 over X times.
I see. Yeah.
And I can't afford, if I try to get more sets than that, I'm going to be in trouble with the set size. But I can get that many.
Thanks for your talk. Can I ask one question about C5? You said that people thought that that case might fail. It didn't turn out to. I wondered, could you say a bit about why they thought that? And also, are there any other candidates beyond C5 where people think that might be a counterexample?
Well, P5 is at least I'm very unconvinced that the theorem's true for P5.
I thought you said it was C, which was the one that people thought was false. But
I think C5, the cycle was the one that was sort of standing out as the candidate for being the counterexample until we proved it. I mean,
so why did people think that though?
2 or 3 people have said that to me. I don't know that it was ever in print, but it's just, it's so symmetric and pretty. You'd think that. I don't know. It looks like it's going to be a counterexample. I don't know.
Okay. Well, I mean, are there any other graphs where people have thought that might be a counterexample beyond?
But P5.
Okay. I see.
Path,
right. Okay, I see. Okay.
I mean, if it was true for P5 as well, I might start believing it.
Okay.